we have a radioactive isotope. And here's what we know. We know that, where'd you go here? It's got a very short half-life. 6 days after finding it, it has 20, there are 20 grams. 20? That's like 20 grams. And then 4 days after that, so, and then actually you could say 10 days after finding it, there are 5 grams. What was the initial amount? How much did we start with? And I actually want to show you 2 different ways you can solve a problem like this, because there are 2 valid ways of doing it. And one way makes more sense to some people, the other makes more sense. So here's kind of the more typical but harder to calculate way. So here's what we've got. I'm still going to use my usual kind of table thing. I know that after 6 days, there are 20 grams. After 10 days, there are 5 grams. And I want to know how many grams are there in the beginning, after 0 days. So I'm still going to use the model. The problem is, for this kind of setup, I don't know what C is. So I'm going to say, well, I've got my model y equal to c e to the kt. I'm actually going to plug in both of these, meaning I'm going to do both 20 equals c, gosh, my writing is really great today, c e to the k times 6, or 6k. And this one will give me 10, God, wow. Sorry, I'm plugging in y. 5 equal to c times e to the 10k. And now the thing about this is it's actually easiest to find k first in this situation. So here's what we're going to do. We're going to solve each of these for c and then set them equal to each other. So I solve this for c. C is equal to 20 divided by e to the 6k. If I solve this one for c, c is equal to 5 divided by e to the 10k. And then we're going to set this equal to this. Let's see, do I have enough room? Not really. I'm going to do it on the other side of the board. So again, this is in the same vein as problems 4 and 12 on homework LPS 24. So I'm going to set the 2 things equal to each other. The 20 over e to the 6k equal to 5 over e to the 10k. I'm going to try and solve for k. So I'm going to cross multiply. 20 e to the 10k equals 5 e to the 6k. Sure. I'm actually probably cross multiplying maybe wasn't the best thing. I'm going to bring my k's to the left. So I'm going to e to the 10k divided by e to the 6k equal to 5 divided by 20. Wow. I'm really struggling to write down the things I'm saying. E to the 10k divided by e to the 6k, we subtract the powers. So 10k minus 6k is 4k. So e to the 4k equals 5 divided by 20 is 1/4. So take the natural log of both sides. The natural log of e to the 4k equals the natural log of 1/4. And so 4k equals the natural log of 1/4. And k equals 1/4 times the natural log of 1/4. Coincidence that it's 1/4 natural log of 1/4. So then to find c, I can plug this back into either one of these equations. So c equals 20 over e to the 6k. So e to the 6 times 1/4 natural log of 1/4. And then you could either use a calculator or simplify this. And this actually does simplify really nicely, believe it or not. 6 times 1/4 is 3/2. This is 20 over e to the 3 halves times the natural log of 1/4. Which, okay, prepare for some simplification here. This 3 halves times the natural log of 1/4, I can write this as e to the, this can come up as the power, and I write this as e to the natural log of 1/4 to the 3 halves power. E to the natural log of a thing is just the thing. This is 20 over 1/4 to the 3 halves power. 1/4 to the 3 halves power is 1 to the 3 halves over 4 to the 3 halves. 1 to any power is 1. 4 to the 3 halves power is the square root of 4, which is 2 to the 3rd power, which is 8. This is 20 divided by 1/8, which is 20 times 8, which is 160. So 160 is how many we started with. This is not my favorite way to do this kind of problem. This is a way a lot of people imagine doing it, where they solve each of these equations for c, set the c's equal to each other, find k, and then plug back in k into either one of these to find c. Let me show you a different way that I think is easier. Either way you want to do it is fine, but let me talk about it a different way. So here's the other way. And I think you'll see that, I hope you'll agree this is easy. Here's what I'm going to do. Even though I've been told that it's 6 hours later when there's 20 grams, I'm going to call this time equal to 0. So at time equals 0, I'm going to have 20 grams. And at 4 hours later, so what I'm going to call time equals 4, or sorry, did I say days? Or I don't remember if it was days or hours. I don't really care. I had 5 grams. And then I want to know so how much I have. Well, I want to know how much I have 6 hours prior. Right? It's okay to make time negative if it suits our purposes. So then I can do this much more easily. I can say, okay, well, y equals c e to the kt. I can say that my c is 20. Now, it's not going to be how much I have at the time I care about, but that's all right. So I can say that y equals 20 e to the kt. Then I can plug in that 4 hours later, I have 5 grams. So 5 equals 20 e to the 4 times k, or k times 4. Solve for k. So 5 divided by 20 is 1/4 equals e to the 4k. Take the natural log of both sides. Natural log of 1/4 equals the natural log of e to the 4k is just 4k. So look, we still get the same value for k. We get k equal to the natural log of 1/4 times 1/4, or divided by 4. So then our model is y equal to 20 e to the k, so 1/4 natural log of 1/4 t. And then we can plug in -6 for t. So we can say, all right, y is going to equal 20 e to the 1/4 natural log of 1/4 times -6. I'm not going to finish simplifying this because I'm just going to show you it's the same thing that we already have. So this is -6 times 1/4 is -3 halves. So this is equal to 20 e to the -3 halves times natural log of 1/4. Well, look, that's exactly the same as this. 20 divided by e to the +3 halves times natural log of 1/4 is the same as 20 times e to the -3 halves times natural log of 1/4. So it's the same thing either way. So I personally find it easier to conceptualize it this way, where I don't have to think about solving for c in this way. I can just say, well, I'm just going to call this time actually time equals 0, and then the time I want to find is back in time, 6 hours or days, whatever I said it was previous. So hopefully that seems reasonable to you. Again, whichever way you want to do this problem, these problems in the homework is fine with me. I just want to point out that there are a couple different ways. Are there questions about either of these before we move on to class M? Oh, sorry, you're breaking up a little bit. Yeah, I can keep it on the board. Sure. All right, go ahead. Go ahead and ask your question. I heard someone say they had a question. You're welcome to try and ask it. You were breaking up a little bit before, but go ahead if you want to.
Can you hear me now?
And yes, you sound great.
I had a quick question because I noticed for homework L, there was a video that was linked underneath the homework that was like an example for, I think it was number 24, or no, it was for number 12 for homework L. There was an example on how to do it. And I was wondering because the way I got C was ended up being 5 over E 1095 times natural log of 1/2 over 276. If we have like if we end up with an equation, do you want us to further simplify to get a single number, or do you want us to just leave it as the equation we get?
I probably want you to leave it. So like if you have C equal to an expression, I don't want a decimal approximation.
Okay, I just wanted to make sure on that.
Yeah, of course.
Thank you so much.
Yeah, I will also point out, thank you, that as mentioned, there is an example of how to do the problem number 12, and it's by Jennifer Healy. Most of the videos that are like already there that aren't our class are from Jen Healy, who is a former colleague. She's a great lady. Her videos are very nice. So if you're looking for help and there is a video, I encourage you to watch it because Jen usually does a very good job of explaining what's going on. I've not watched all of her videos, but I have watched some of them. And the ones I have watched, she definitely does a nice job of saying what's what. All right. So moving on to class M. M for piecewise functions, right? Piecewise does not start with M. They couldn't hold out till P, I guess. Oh, well, that's fine. So class M, piecewise functions. And let me see if I want those ones or I want these ones. Both my notes are pretty good. Okay. So piecewise functions are pieces of different functions all graphed on the same XY coordinate plane. Let's look at the following. Scale is gross. Got stuff in my hands. Let's look at f of x equal to. So usually piecewise functions have a large brace like this, a left brace. It's equal to x squared plus 1 when x is less than 2. And it's equal to 7 minus x when x is greater than or equal to 2. We want to graph it. So what's going to happen here is the graph of this is going to look like x squared plus 1 to the left of 2, to the left of x equal to 2. And it's going to look like the line 7 minus x to the right of x equal to 2. So let's actually look at each of those individually. So x squared plus 1 is pretty straightforward. It's the usual x squared graph, shifted 1 in what direction? Up, down, left, or right? Somebody. If we add 1 outside the function, it's going to shift us up. Okay, so like if we just wait long enough, he will say it. That is probably usually true because we have limited time. So here's y equal to x squared plus 1. And then 7 minus x, well, I was going to do 7 minus x in a different color. Sure. We'll do the axes still. The same one. So 7 minus x is going to have a y-intercept of 7 and an x-intercept of also 7. All right, we set x equal to 0, y is 7 minus 0. So we get the point 0, 7. And we set y equal to 0, 0 equal to 7 minus x. If we add x, we get x equal to 7. So we get the point x is 7, y is 0. And so the line just goes to those 2 points. So for a piecewise function, what we have to do also is kind of look at what is happening at the place where you change from one piece to the other. So 2 is where things are changing, right? It's this function to the left of 2, this function to the right, this function to the right of 2. So let's see what's happening at 2. So 1 and 2. So when you plug in 2, I can just plug in 2. 2 squared is 4, 4 plus 1 is 5. So this is the point 2 comma 5. And when I plug in 2 here, let's see, 7 minus 2 is also 5. So this is kind of what feels like the nicest case, where the left-hand portion and the right-hand portion are going to match up. So what we're going to do, in fact, I'm just going to erase the parts I don't want. So when we graph this in one graph, I'm going to want everything from x squared plus 1 to the left of 2. So I don't want any of the stuff to the right. And I also don't actually want this point here. I want everything to the left of 2, but not actually equal to 2. So I want all that. And then I want, for the red graph, everything to the right of 2, including 2. So everything bigger than or equal to 2. So I don't want any of this. All right, so here's 2. For this graph, I want everything that's to the right of 2, including 2. For this graph, I want everything that's to the left of 2. And so when I draw the piecewise graph, which is just both of them put together on the same plane, maybe I can fit it down here, yeah. So we'll try and be somewhat precise here. 1, 2, 3, 4, 5, 6, 7. I just got a text message. I don't know who is contacting me, but someone gets weird on it. Anyway, sorry. So my parabola, right, does this. There's the point 2, 5 that it doesn't have. It also has the point, I guess, 1, 2, if you really want that one. So it looks like this. Also, we should draw an arrow like that up to the left to indicate that it keeps going. And then this graph also has the point 2, 5. So even though it was an open circle from this one's going to fill in that open circle. And then we're going to have everything to the right. So it's going to hit the point 7, 0. So there's the graph of f of x equal to x squared plus 1 when x is less than 2, and 7 minus x when x is greater than or equal to 2. And if I was graphing this, like if I was doing this as a homework problem, I would be sure to label all the intercepts. So definitely the point 0, 1. Definitely the point 7, 0. 0, 7 is no longer an intercept because even though it wasn't a y-intercept for this graph, you don't get the y-intercept of this graph because you only get this graph when x is bigger than 2, which doesn't give you when x is equal to 0. I would also label this point where we change from one graph to the other. Questions about this?
I had a quick question.
Go ahead.
When doing the homework, is it fine? Do we have to specifically label like the point where it changes, or if we were to differentiate with the different color, like the two graphs, or do you want the point?
I do want it to be, yes, labeled would be good, or it should be really, really easy for me to read what the point is based on your if it was very clear that this was 1, 2, 3, 4, 5, 6, 7, and I could see that it was crossing there, and I could count them, and it was not impossible to see what it was, that would be fine. But it's probably better to just label them so that there's no confusion. So yeah, I would say label them. And yes, this point as well, for sure. Let's look at another example. A very similar example. How did I find the point 2, 5? So for each of these graphs, so basically, here's what I did. I said, hey, look, the pieces are changing at 2, right? I get this piece all the way up until 2, not including 2. And then I get this piece after 2. So I should really look and see what's happening at 2. So what I did was I plugged in, so even though this graph isn't defined, this piece isn't defined when x equals 2, I still plugged in 2 to figure out what it was getting closer and closer to, right? If I plugged in like 1.999999999, that number squared is almost 4, and this is almost 4 plus 1 is almost 5. So I'm getting, as x is closer and closer to 2, this function is getting closer and closer to 5. Similar idea here, except we can actually plug into, I mean, we actually plug in here too, right? Plug into, you get 5. So basically, where things are changing is always a place you want to think about graphing what's happening there if it's a piecewise function. We'll see that's true for the next one as well, for all of them, really. So let's graph the piecewise function, which is going to be very, very similar to the one we just did. It's going to be slightly different. F of x equal to, instead of x squared plus 1, we're going to have x squared when x is less than 2, and still 7 minus x when x is greater than or equal to 2. So the difference here is that the parabola is now just the regular parabola, which has, you know, the point 0, 0, the point 1, 1, and the point 2, comma 4. And then the other function is still the same as it was before, right? We still have, trying to draw them so that they're similar to the shape, right? Sure. We have the y-intercept of 0, 7, we have the x-intercept of 7, 0, and we have the point 2, comma 5. So the problem is, or maybe not the problem, but the difference here is that now they're not going to meet up at the 0.25, right? This one we're only getting to 2,4, and this one we're getting to 2,5. So when we try and graph a piecewise function, there's going to be some discontinuity, which is okay. It's fine for a function to be discontinuous. So let's see what we get. And so you don't have to, like, I'm going to draw them and then I'll erase the pieces. You don't have to erase anything. You don't even have to draw these pieces separately. So typically, I kind of ideally like to just draw it all on one graph. But the idea is I want the left piece of this. So I want everything to the left of 2. So everything this way, meaning everything this way. Right, I want all of this. I don't want any of this stuff up here. Let's see. So 1, 2, 3, 4, 5. So yeah, I want. So here's the thing. I don't actually get the point 2, comma 4 though, right? Because if I plug in, I can't plug into here. Actually, I can plug in numbers close to 2, like 1.99999, and get numbers that are close to 4. So I get an open circle at the point 2, comma 4. 1, 1, and 0, 0, and negative 1, 1, and so on. So there's my usual parabola, y equals x squared, ending just less than 2. And then I get this line starting at the point 2, comma 5, right? So again, starting at 2 and going to the right. All of this, I don't want any of this up here. So here's the point 2, comma 5. Oops, I should do it in the same color though, because I usually like to graph my graphs in the same color. I mean, it's not a huge deal. But here's the point 2, comma 5. I'm just going to go down this way. And this will be the point 7, 0. This is obviously, you don't have to label the origin. I'm not going to label the origin. You can if you want to, but if it goes to the origin, it's pretty obvious it's going to the origin. So the other points I should label though are both the point 2, comma 5, and even though it's not a point, we should label a hole as well to indicate that the graph is getting close to that point, but it doesn't actually hit that point. So this would be the fully appropriate labeled piecewise function, f of x equal to x squared when x is less than 2, f of x equals 7 minus x when x is greater than or equal to 2. And so at any kind of break or junction, when you switch from one piece to the next piece, if they don't meet up, you should label both the left-hand piece and the right-hand piece, what point each are getting close to. Questions? Okay, let's look at some more. I don't know what I was doing. I was looking for more examples because I'm definitely gonna. I think there's not a whole ton of examples on this homework on this class. So yeah, okay, there's some more examples I can draw from. mean, I can also make them up, but it's good to have nice examples that are already pre-made up instead of making up my own and then making something that looks kind of terrible. So let's do an example where we're going to graph the thing without actually graphing each piece. But then we'll go back and graph each piece. So here is our piecewise function. It's got 3 pieces. F of x is equal to x squared when x is less than or equal to 0. It's equal to x minus 1. And I'm going to make a small mistake here on purpose, and I'll go back. So right here, I'm making a mistake. X is greater than or equal to 0, less than 1. And then it's equal to the natural log of x when x is greater than or equal to 1. And here's the small mistake I've made that's kind of a big deal. I've accidentally defined this function to be 2 different things when x is equal to 0. I've defined it to be x squared when x is 0. I've also defined it to be x minus 1 when x is 0, which actually means it's not a function. Because if I plug in 0, I'm going to get 0 and I'm going to get negative 1 for y, which violates the rules of being a function. A function means that if you plug in an x value, you get only one y value out. And the way I actually went to define the function was for x to be strictly between 0 and 1 for this middle piece. So now it's perfectly fine. We're not defining the function to be different things for the same value of x. So let's graph it. And I'm going to try and just graph it in one shot, meaning I'm not going to graph the 3 different graphs separately and then put them together. We will after to kind of see. So here's how I would do this. I would start from left to right. Most of the time, if a person is writing a piecewise function for you, they're going to write the pieces in order from left to right, right? So this is the leftmost part when x is left of 0. This is the middle part when x is between 0 and 1. And this is the rightmost part when x is bigger than 1. So it looks like x squared when x is less than or equal to 0. Great, we know what the parabola looks like. It's y equals x squared to the left of 0. So it's going to give me the point. You don't have to be, like, I would probably just graph it like this. I'm going to try and draw a nice graph for you guys because it's nice to have nice graphs sometimes. I like that I tried to graph it and then totally missed the points I plotted. Okay. So there's our y equal to x squared when x is less than or equal to 0. So I do get the origin here because when x is 0, if x is 0, I plug in 0, 0 squared is 0. Speaking of which, let me see one thing here. Sorry, one moment. Let me do that. So I can get that. Cool. It's equal to x minus 1 when x is between 0 and 1. So I know that x minus 1 looks like a straight line going up from left to right. It would have a y-intercept of negative 1, but I can't quite plug in 0. So I'm going to get an open hole there. And then when x equals 1, if x could equal 1, I would get 1 minus 1, which is 0. But again, I don't get to fill that in because it's almost 1, but not quite 1. So it's a straight line from 0, negative 1 to 1, 0. But I only get that portion, right? I don't get the parts that, right? Normally, the line y equals x minus 1 would look like this, right? I'm just getting the segment of it that's between 0 and 1, a very tiny piece of it. And then the last part is the natural log. So I know that the natural log of x, right, looks like this with a vertical asymptote at 0. But I know that starting at 1, well, I know that if I plug in 1, what's the natural log of 1 equal to? I would like someone to type or tell me the answer. What is the natural log of 1? So I didn't quite catch that. Say again.
Would it be e or 0?
It is one of those. So the base is e. So it's log base e of 1, and it is 0 because e to the 0 is equal to 1. So what that does for us is it actually lets us fill in this hole here, right? So we had an open hole at 1, 0, but now when x is 1, we actually do get 0. So we fill that in. And then we draw the rest of the logarithm that looks like this. So that's what our piecewise function looks like. I should label a couple things. I should label this x-intercept as 1, 0. I should label this hole, right? It's not a y-intercept because we don't actually have the point, but I should still label this because it's the end of one of the pieces. as 0, -1. We do not need to label the origin. I will point out, right, if you wanted to, we could have totally individually graphed all the pieces, right? So here's y equals x squared. I'm not graphing them very well. Here's y equals x minus 1. And here's y equal to the natural log of x. And then we're taking these parts. I want the, when x is less than 0, less than or equal to 0, so I want that. Here I want when x is between 0 and 1, so I just want this tiny little segment here. And then here I want when x is bigger than or equal to 1, so I want all of this. So putting this and this and this together in one coordinate system gives me that. And what I want to say is you are never required to graph all the pieces individually. If you can get to this, that's perfectly fine. But if you want to, it is always perfectly fine to graph the pieces individually and then identify which parts of those different graphs you want and then put them all on one coordinate system. You do have to put, so I will say, your final answer does need to look like this. It shouldn't have any more than this, right? There shouldn't be extra pieces on here, and it shouldn't be any less than this, right? We should have exactly this graph at the end result. But the intermediate steps to get there, whatever you want, is fine.
I had a question.
Yeah, go ahead.
So we would label the holes specifically like where they are. So like I'm kind of confused as to why the parabola wouldn't have any holes. It's just because it fits into like the restrictions it has.
Well, the parabola doesn't have any holes because it's so basically you're often going to get a hole for the pieces that have x strictly less than or strictly greater than a number. But if it's less than or equal to, so basically since x can be less than or equal to 0, I get to actually plug in 0, and 0 squared is 0, so I do get this point here. Let me show you how this would change just slightly. If I don't love that, but I'm gonna change it slightly just to kind of show you the difference. So what if instead I said it was x less than 0 here and x greater than or equal to 0 here? Well, then I would end up filling in this point, because when x is 0, 0 minus 1 is -1. I'd still label it though. And I would end up getting a hole at this point. Because now I don't get to have, say, x is 0 for this piece. It's almost 0, right? It's really, really close to 0. It's like -0.00001. And if I plug in -0.0001 and square it, I get a number that's very, very small, right? So I'm super duper close to that, but I don't quite ever get to 0, 0. But the holes are always going to occur at places, if they occur, where you have x strictly less than something or x strictly bigger than something. I don't have that in this particular example, but that's where they potentially can occur.
Okay, thank you.
Welcome. And I'll definitely point that out in the next examples, which I will now look at. Yeah, I still got 14 whole minutes here. Let me actually look ahead just to see one thing. Oh, come on. Sorry, one moment. We will do more examples. I just want to look at what's class N, just to think about what's coming up here. Oh no, we can hold off on that for a moment. Oh, and there definitely is one other piecewise function I for sure want to graph that is super duper duper important, but that one we will not do just yet. So let's grab some examples here. Yeah, let's look at what do I want? Oh, we should definitely do one like that. Yeah, okay, and we should definitely do. Let's do. Sure, let's do this one. Let's do. Yeah, let's do f of x equal to x cubed plus 1 when x is less than 1, and the square root of x when x is greater than or equal to 1. Okay. So I know what each of these functions look like. I know what a square root. In fact, here I probably would draw them out. So I know that x cubed plus 1 looks like your usual cubic function shifted up 1. So instead of getting the point 0, 0, I'm going to get the point 0, 1. So it's going to look something like this. There's your x cubed plus 1. And the square root of x we know looks like this. I'm really interested in what's happening where we change. So what's happening at x equal to 1? Well, for this one, when I plug in 1, 1 cubed plus 1 is 2. For this one, when I plug in 1, the square root of 1 is 1. Since I'm not getting the same y value, I know there's going to be a disconnect or a discontinuity. Come on. So let's see. So I know I care what's happening at 1. So let's see. So I have this graph x cubed plus 1 when x is less than or left of 1. Since this is the less than and not equal to, this is the graph where you're going to get the whole if they're not connected. So I know I'm going to get a whole at 1, 2. And then this graph has a y-intercept of 1. It also has an x-intercept of -1, because if you set x cubed plus 1 equal to 0, you get x cubed equal to -1, and the cube root of -1 is -1. So this left piece looks kind of like this. And then, right, you guys know my cubic graphs are never good. And then the right piece, I'm just going to get everything from this point onward. So I'm going to get the point 1, 1, and then it's going to look like the rest of the square root graph like that. And I should label this point as 1, 1, and this open hole as 1, 2. And I should label the x-intercept as -1, 0. Again, right, if you start, so I would definitely say label these points where you have like things changing from one graph to the other. Your intercepts, you might not want to actually label on the graph. You might want to write, right? Because I feel like things are getting a little too messy here. So I might write like somewhere else like x-intercept, -1, 0, y-intercept, 0, 1. Or if it's really, really clear from your graph, right? Like I've marked things off so that, right, this is -1, this is -2. I think if it's clear that your point is going through the point that is -1, you don't actually have to also label it. Just make it super obvious what your things are. Let's look at another example. We got time for at least 2 more examples. Piecewise functions definitely come up a lot in like the first, I want to say maybe 2 or 3 weeks of calculus, the first quarter of calculus. When we define continuity, they are prime examples of functions that are discontinuous. So the first one we did today, when it was, you know, the parabola and then the 7 minus x where they met up, that was a continuous function, right? There were no jumps or breaks or anything. But the 2 examples after that, and this one as well, are all examples of functions that have a discontinuity, because we're going up here and then we get to this point and then we have to jump somewhere else to that. So if you have to lift your pen off the board or your pencil off the paper to graph the thing, that means we most likely have a discontinuity. Whereas if you can graph the thing without doing that, like here, right, I can graph the whole thing without lifting my pen off the board, then it's continuous. There are more formal definitions of continuity, which you will definitely learn when you take calculus. But for now, that's a good general idea of what it means to be continuous. Let us look at this example. Let's look at f of x equal to, I think I'm going to change this one just a tiny bit. Sure. Yeah, let's say it's x squared minus 1 when x is less than 2 is equal to 6 when x is equal to 2 and is equal to, what do I want here? Sure, the square root, why not? The square root of x plus 7 when x is greater than 2. All right, so again, we know what all these things look like. X squared minus 1 is your usual parabola, meaning the one with the vertex at the origin shifted down 1. I'm not even going to bother with this for a second. And square root of x plus 7 is the square root function shifted 7 to the left. So I'm really, really interested in what's happening at 2. So if I plug into the x squared minus 1, even though I know I don't quite get there, 4 minus 1 is 3. So I know that at 2, right, so if I plug it, right, so I'm going to get my usual parabola. It's going to do this kind of thing. Oh, sorry, it shifted down 1, right? So I'm going to actually hit that point there. I'm going to, sorry. My intercepts are a little bit different. So this is going to have x-intercepts that are -1 and +1. So I probably overshot my error. I should start. Let's just do this. And then we should still, right? We shouldn't just stop the graph here, right? We should actually say, oh yeah, the graph does keep going that way. Let's ignore this for 1 second. Square root of x plus 7, if x is bigger than 2, well, if x was equal to 2, 2 plus 7 is 9, square root of 9 is 3. So we would actually get the same value. So square root of x plus 7 basically looks like the square root graph shifted 7 to the left. So it's going to be like this, and then it's going to start right there. Right? My square root graph, square root of x plus 7 would look like that. And then here's the point, like 2, 3. I'm just taking this portion of it. Okay, so people kind of get thrown off by this middle part here. So if I said graph f of x equal to 6, you graph a horizontal line, y equal to 6, the whole way through. But I'm saying f of x equal to 6 only when x is equal to 2. Well, that's just a complicated way of saying we've got the point 2, 6. So there's my graph. It's kind of annoying, but that's what it is. Yeah, we've got a hole at 2, 3. We have this other point at 2, 6. I would also say this graph is discontinuous, right? Because even though I can almost graph the whole thing without lifting my pencil off the paper, I do have to lift my pencil off the paper to get that one point. Again, don't worry about like if something is continuous, discontinuous. I'm just trying to prep you for what's coming in the future, right?
James, where did you draw the 6?
So, right, so right here. Right, because the function is equal to 6 only when x is equal to 2.
Okay, that makes sense.
Sure.
Thank you.
Let me show you a slightly different version just to kind of point out something else. So let's say the function was instead, what have I got? Let's say f of x equals, trying to do something slightly different here. Yeah, let's say it's 1 over x when x is less than 0. Let's say it's 3 when x is bigger than or equal to 0 and less than 2. And let's say it's, I don't know, something like 9 minus x squared when x is bigger than or equal to 2. So it's 1 over x when x is less than 0. So 1 over x looks like this. The rest of it looks like that. But we don't get that part when x is greater than or equal to 0. F of x equal to 3, I know my writing is not great. When x is bigger than or equal to 0 and less than 2. So when x is 0, we get 3. And then it's just the constant horizontal function, 3, all the way from 0 to 2. Except at 2, since it's less than 2 and not less than or equal to, we're going to get an open circle there. So we get the point, right? That's the point 2, 3. Right there, or it's the whole 2, 3. And then we get 9 minus x squared, which looks like a parabola, except it has been flipped over, so it's opening downwards, and it's shifted up 9. So I know it's going to do something like this. I'm going to figure out what's happening at this point here. When x is 2, 9 minus 4 is 5. So I get the point 2 comma 5, and it kind of looks like the parabola coming down this way, and then it actually starts there. And it would have an x-intercept of positive 3. Because if x is 3, 9 minus 9 is 0. So here, if you've got f of x equal to a constant and it's more than just one value of x, you get more than just a point. You get a whole horizontal line segment.
Can I ask a question?
Yes, of course.
Can you explain one more time how you plotted the second aspect of the piecewise function?
This part here, the f of x equal to 3?
Yes.
Sure. So y equal to 3 or f of x equal to 3 or any constant value is always going to be a horizontal line, because no matter what x is in this domain, if x is 0, y is 3. If x is 1, y is 3. If x is anything in between 0 and 2, y is 3. So when it's a constant, you just get a horizontal line at that constant value. And then if x is 0, I do get the point 0, 3, and then all the way up until 2, but not including when x is 2, I get all the y values being 3.
Right, and that's why we have an open circle.
Correct, because it's x less than, not less than or equal to 2, right? If instead the graph was like this, where it was a less than or equal to here and a strictly greater than there, then we would have the hole up here. Oh, I should have labeled that point. I'd have the hole up here at 2 comma 5. I should have labeled this whether or not it was a hole or actually filled in. And this would be filled in if it was defined like this.
Thank you.
You're welcome. All right, I know it's 11:50, but I just want to throw one more super duper quick example at you. It'll only take a second, I promise. So the last one that you already know is f of x equal to negative x when x is less than 0, positive x when x is greater than or equal to 0. So this last example, I'm going to actually do it from right to left. So if f of x equals x, that's just y equals x. It's a straight line that looks like this. When x is positive or 0, when you plug in 0, you get 0. And then when x is negative, so over here, you get y equals negative x, which looks like this straight line. What's another name for this function? It's the absolute value of x. So what I really want to say, and I want everyone to know this because this does come up with somewhat regular frequency in Calc 1 and 2, is that the absolute value of x is a piecewise function. It's defined to be negative x if x is negative, and it is just x if x is already non-negative. So just something to be aware of.